So what we're going to go through first are exponent laws, which we talk about a lot in grade 10 and then very little in grade 11, which is slightly annoying. Exponent laws. So one of our exponent laws is this. If I give you x of A times x of B, what do I get? Two bases that are the same, two exponents. X A plus B. So when you have two bases that are the same and two exponents, you add the exponents. So we're going to get x A plus B. An example of that would be x to the 3 times x to the 6. What would I get? X to the 9, not 18. So if this one I add, does anyone remember what it would be with x and a's and b's as exponents that would cause me to multiply? Yeah. So if we had x to the a all to the b. So when we have two bases and two exponents, we can put them together if they're the same base, correct? So if I had like x a y b, it would be x a y b. I couldn't put them together. They have to have the same base. Same base, two bases, two exponents, you add them. One base, two exponents, you multiply. So with this would get me x a b. No one messes that one up. They just try and multiply the other one as well. So an example would be x to the 2 and a 3 outside. What would this be? X to the 6. Where do you think I would subtract? Yeah. So if I had x to the a divided by x to the b, that would be the same as x to the a minus b. But they have to be the same base. They would both have to be x, correct? So an example could be x to the 4 divided by x to the 1 is x to the 3. Another exponent law you were given in grade 10. X to the 0 is 1. Anything to the 0 is 1. I used to do this in grade 10 all the time, but I haven't got able to teach grade 10 in so long. Ooh, making them fluffy. Sure. Nah, I don't want fluffy. He's a pig. James, don't be jealous of my art skills. What is piggy to the 0? 1. Big. Now, why does that work? Why does to the power of 0 work? Well, let's do a pattern just to prove why it works. So, if I have, let's say, 3 to the 1, what does that equal? 3. And 3 to the 2, 9. And 3 to the 3, 27. Okay, and it's going to keep growing exponentially, right? Faster, 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 faster. That's part of exponential growth. Now, what if I do 3 to the negative 1? It's a third. This is another little rule we're going to give. Remember, you can make negative exponents positive by, if they're in the numerator, moving them to the denominator, and if they're in the denominator, moving them to the numerator. So if we have this, we can take this and we can drop it to the bottom, and we're going to get 1 over 3 to the 1, which is a third. 3 to the negative 2, how could we rewrite that?
1 over 9.
Yeah, 1 over 3 to the positive 2, which is 1/9. And what buffer's in the middle of that? 3 to the 0, which is 1. Because you're literally just multiplying by 3 to get to the next one. So 1/9 times 3 is a third. 1/3 times 3 is 1. 1 times 3 is 3. 3 times 3 is 9. 9 times 3 is 27. So that's why anything to the power of 0 actually just results in 1. I do not know what's going on. It's probably better that way. Okay. So does it make sense why anything to the 0 is 1? So what if I give you this other rule? So we just said x to the negative 2, I could rewrite as 1 over x to the 2. We agree? Everyone told me that's fine. If I move it all to the bottom, it could take the exponent with it. So an example, if I have 8x to the negative 2 over y to the negative 3, is that negative 2 on the 8 or on the x? On the x. Is the 8 negative at all? What is the 8's exponent? 1. So actually, the 8's exponent is a 1. So are we going to move that at all? No. Do we need to move the 8? No, it has a positive exponent. So you don't move the 8 with, which is what the big error in grade 10 is all the time. So you're going to take the x to the negative 2, you're going to bring it down here, it's going to become x to the positive 2. You're going to take y to the negative 3, and you're going to bring it up here, and it's going to be y to the 3. So we're going to get 8 y cubed over x squared. So those are the grade 10 rules we learned, correct? Now, you have. Agreed. Okay, so now what we actually have to do is we have to use these rules in the entire exponents and logs unit. So, together. The first thing that we're going to do is we've learned how to solve linears in grade 10. We learned how to solve quadratics and rationals and radicals in grade 11. And then in grade 12, we learned how to solve polynomials by doing synthetic division, right? We're also going to learn how to solve exponentials. And we've never had to do that before. We've never had like 3 to the x equals 7. We've never had a variable in our exponent before, except for a little bit in geometric series and sequences in grade 11. But for the most part, we haven't. So we have to figure out how we can solve those. So we're going to solve by common base first. And what are we solving by common base? Exponential equations. And when we get the word solve, it doesn't matter what unit we're in math. It doesn't matter what even course we're in math. If it says solve, ultimately what it wants is variable equals number. What the heck does the variable equal? That's what solve means. It doesn't matter what unit we're in. It means x equals what or n equals what, whatever the variable is. So we're going to do solve. Number 1. So I'm going to give you 3 to the x plus 2 equals 9. Really easy one. They don't say this way, but we're going to start this way. You will find it easy. A caveat off to the side. If I give you this, if I say 3 squared equals 3 smiley face, 3 to the smiley face, what could you tell me smiley face equals? 2. You'd like, no doubt, you're an idiot. Of course it's 2. This is 3 to the 2. This has to be 3 to the 2. Smiley face has to equal 2. We agree? This one's easy because they have a common base. Oh, solve by common base. Weird. That's how this lesson's going to go, okay? So, if I can make both sides have the same base, then what can I say about the exponents? That they're the same. They're equal, correct? So I always try and make them be the smallest base. So I have 3 and I have 9. Now I'm not going to multiply to make the same base. I'm going to do exponents. So what can I make 9 be? 3 to the what? 3. 3 to what exponent? 2. Right? And I try and make them be smaller. I don't make 3 be 9. I will always try and make 9 be 3. Yeah. Yeah. So we're going to get 3 to the x plus 2 equals 3 to the 2. We agree? 9 to 3 squared. Now if they're the same base, what can I say after this point? The exponents should be equal. So what am I saying? I'm saying that this should equal this. So I'm going to say that. X plus 2 equals 2. And then I just have to solve. Minus 2, x equals 0. And then I always check. If it's algebraic, whenever you solve, the great thing about solving is you can always check it. So we're going to go 3 to the 0 plus 2 equals 9. 9 equals 9. When you check, nothing on the left moves to the right, nothing on the right moves to the left. And I know I'm right, I'm done. Okay? Wouldn't it be nice if it stayed that way and that easy? But it won't. That's just the gist of it. So our goal when solving by common base is to make the bases the same, and then the exponents just equal, and then we solve it out. Okay? What if I give you this? I'm going to go 9 to the x plus 1 equals 27 to the 2x minus 1. So the last one, I could make the 9 be a 3. We agree? Can I make the 27 be a 9?
You can make it a 3.
I can't make the 27 be 9, but I can make them both be base 3. So sometimes neither base works, but they have a common base that you can make them be. 9 is 3 to the what? 2, and 27 is 3 to the what? 3. You need to make sure you put the other part of the exponent in brackets, because that 2 has to go to both of them, correct? And then 27 is 3 to the 3. And then I have to make sure I distribute, because this is where the error happens, is people forget to distribute the 2 to the 1 over here. So I get 3 to the 2x plus 2 equals 3 to the 6x minus 3. Now if they're both base 3, what can I say? The exponents have to equal. So my next step always is to then write my exponents equal to each other. Because if this is 3 to the this and this is 3 to the thises must equal. So I'm going to have 2x plus 2 equals 6x minus 3. And then people get stuck here. If you have two x's, one on each side, don't spend more than 30 seconds figuring out which one to move. Take one and move it. Because you need your x's together. So I'm going to minus 2x. So I'm going to get 2 equals 4x minus 3. Then I'm going to add my 3. I get 5 equals 4x. Divide by 4. And x equals 5/4. Then we can check it. And you have a calculator that you can punch it into. Where do we check it into? We always check it into the original. Not something we've touched, because not everything we touch turns to gold. Correct? So we're going to put it into the original. I am speaking for myself. So 5 over 4 plus 1. Type that in brackets, because that's the only way your calculator knows it's. And then on the other side, you're going to go 27 to the power of 2 to 5 over 4 minus 1. Now, if you have the old calculators, if you have the TI-83s, the only way you can type this into your calculator is if you use brackets on the exponent, because it's going to go like 27 to a little roof symbol, and then you have to put the entire exponent in brackets. If you're someone who has a calculator where your exponent pops up, good, just type it in, you're totally fine. But if you have the older calculators, you're going to have to put this whole thing in brackets and that whole thing in brackets. to make it raise to that if you have TIE3s. So everyone's trying it out to see if they match. Everyone has to practice with their calculators. I'm really good with mine, but I'm not using mine for you on your test. I'm not. Did everyone get the same decimal on both sides? Hmm? You're going to try this one out yourself. 8 to the 2x plus 1 equals 16 to the 3x plus 2. Okay, so we're going to get 8 is 2 to the 3, to the 2x plus 1, and 16 is 2 to the 4, 3x plus 2. So we're going to get 2 to the 6x plus 3 equals 2 to the 12x plus 8. And we set our exponent, 6x plus 3 equals 12x plus 8. Subtract 6x or subtract the 12, it doesn't matter, you're still getting the same answer in the end. 3 equals 6x plus 8. Subtract 8. Negative 5 equals 6x. And then sad when people get to this step and then in their head they don't do the last, like divide by 6, and they flip them. And they tell me it's 6 divided by negative 5, which is the saddest thing ever. So, please don't skip this step, because this is honestly where the biggest error happens. People flip them just in their heads. So it's negative 5 over 6. And then we should never walk away wondering if we're right, because we can check them. Correct? Now, I'm going to teach you something else. Type 8 to the 2x plus 1 in y1 and 16 to the 3x plus 2 in y2. Nope. Just type it into your y1 and your y2. When you're done, go zoom 6, just to set your window back. Very top middle, zoom, and then standard. Just makes it back to the standard window just in case you weren't there. Can you see two graphs crossing? You're going to try and find out where they intersect. So go second, trace, 5, enter, enter, enter. You don't have to move it around, just go enter, enter, enter. Second trace 5, enter, enter, enter. Now, did you get an X at the decimal of some sort? Okay, how do we get it to our main screen to figure it out as a fraction? Do you remember? Go second mode, one right beside it, second mode, gets you back to your main screen, and then go X, enter. And then math, enter, enter. It should be negative 5, 6. So we have 8 to the power of. Now if I say algebraically, which I always will, and you give me an answer off your calculator, how many marks are you getting? None. Because you didn't know algebraically. So we go second, trace, 5, enter, enter, enter. And it gives me this 0.8, negative 0.83333, whatever that may be. I go second mode, X, enter, and then math, enter, enter. Ah, it's the same answer. Well, I'll be darned. Look at us winning.
I think that takes way more.
Well, it's a good way to check. One last little type. What if I do this? What if I do this?
Ain't happening.
It's way easier than it looks.
Girl, please.
What? Don't use my own sayings on me. Okay. What base can we make them both be? If we just had 8 and 4, what base can we make them both be? We can make them both be base 2, right? 8 is 2 to the 3, 4 is 2 to the 2, correct? Okay, that's 8. 8 is 2 to the 3. We all agree. Yeah? Now type in your calculator 2 to the negative 3. Math, enter, enter. What is 2 to the negative 3? 1 over 8. Now why is that? Because I can bring the 8 up, or I can flip a fraction by raising it to what? The negative 1. So in order to get rid of a negative, I can move it to the bottom or to the top and it'll become positive. If I have a positive, I can move it from bottom to the top and make it negative, right? So if I know 8 is 2 to the 3, 1/8 is actually 2 to the negative 3. And then 4 is 2 to the 2. How can I check it? Algebraically, I can plug negative 5/12 in there and just type in my calculator, right? Or y1, if I want a fraction, I have to put it in either alpha y equals enter and get a fraction, or I have to put it in brackets. Everyone's trying it out in their calculators. Guess what tonight's homework is?
No homework.
You remember those unit summary sheets?
No.
Yeah, work on yours.
Oh.
Yeah. I think it's the transformations and radicals and rationals. Trust me, majority of you need to do the summaries because your transformations are still getting flip-flopped. And you don't remember what's in radicals and rationals. So you need to do a summary sheet. It doesn't need to be extensive, like 70 pages long. It just needs to cover each of the different topics. So for transformations, you could literally go words, mapping, equation, right? And then you go inverses. And then you have to do radicals. Radicals is, if I give you a radical, what are the transformations? Or if I give you a function, a linear quadratic, can you take the square root of it, right? Rationals, we did transformations of rationals, and then we did the one where I gave you the 3 steps: numerator smaller than denominator, numerator equal to denominator, denominator or numerator less than numerator equal, numerator greater, and points to continuity. In those words, I just explained the whole tooth for you. Like, it doesn't need to be 18 pages long. It just needs to cover all the different things.